Oh, hello, everyone. Excellent work on your first exam for those of you who weren't disrupted by horrendous bomb attacks. I'm really sorry to hear about that. Hopefully everything will be sorted. I wouldn't panic too much. I'm sure the QCAA will sort that out without any unfair disadvantage. So just try and clear your mind of it and look forward to what's coming tomorrow, and let's try and do our best with those ones. So feel free to post any requests in the chat. I've also made an email address here, so you can post, you can email me any, like if you've got any particular questions that you're stuck on that you want me to do, you can send them there and I can put them into my OneNote here. Okay, but I thought probably go another Hungarian algorithm question because, I don't know, I just have a feeling in my bones that there's going to be a Hungarian algorithm question tomorrow. And then I was thinking maybe some critical path analysis as well. See how we go with that. And yeah, send any other requests. All right, so if we're happy with that, why don't we make a start on the, I'll go over residuals. Yeah, that's a good one. Okay, yeah, there was one on the mock about that. So we can definitely do that one. Let me just get that one ready while people are still filing in. Yeah, go ahead. Send me the question about the weighted graph. You can just send it to that email address there, or you can post it on the in the chat of that Facebook group, and I will find it there as well. Just let me know what you've done. Yes, Sam, definitely we'll have a look at Hungarian tonight. I've pinched one already from the sample IA2, so we'll have a look at that one as well. Okay, let's make a start then. Okay, so let's start with that residual question that was on the mock. Okay, and this is a good opportunity to talk a little bit about bivariate data analysis in general. Okay. Yeah, excellent. Okay, and a question about deseasonalized data as well. I have done time series deseasonalized data questions in the last 2 live streams. So if we don't get to them tonight, they'll be on those videos from the last sort of 2 that I did as well. I'll try and get in and put timestamps to some of those questions, but I haven't really had the time. But what we're about to do now is almost exactly the same procedure that you do for coming up with the least squares regression model in time series data. So very, very similar process. So that'll be helpful. Okay, so you can pretty much guarantee that you're going to see some bivariate data. You're going to see some data in tables tomorrow. So it's a pretty safe bet that when you see data tables like that, you're going to need to enter them into your calculator. Okay. Yeah, we can definitely try looking at reducing balances as well. But like I said, we're a little bit, I don't want to keep you up all night tonight. So if I don't get to it, we did both the last two live streams as well. In fact, one of the things we were talking about last night about geometric decay apparently came up quite strongly on the test today, something about birds declining. Oh, my email address, I'll put that back up again. Yeah, so if we don't get to reducing balances tonight, definitely hop over to this YouTube channel basically and have a look at yesterday's live stream, and you'll just kind of click through it and you'll find it there somewhere. Great. Okay, so on this question here, the first thing you're going to need to do is put that data into your calculators. I'm using the green calculator. So go ahead and do that if you haven't already done so you can see what I'm doing. They very helpfully tell you which variable is which, so that's nice. Okay, I've entered my data in. I'm scrolling down till I find the A and B values. Okay, so the first thing I need is my least squares regression line. Okay, so that looks like this. Okay, now bear in mind that when you're looking at A and B on your calculator, it's the wrong way round on those green calculators, okay? So you got to switch them around when you put them into the calculator, okay? So that's going to be y equals, or you can even change that to temperature if you want. Okay, you can do that, or you can use X and Y if you prefer. Okay. So now what I have to do is I have to come up with predicted values for each of my X variables. Okay, so basically what I'm going to do is I'm going to add another column here. Okay, so my predicted values, the prediction comes from the equation that I just came up with. Okay, so go ahead and figure those predicted values out. So I had a question, would you stress about knowing how to create a payment schedule for annuities in the withdrawal phase? I know what you're talking about. I haven't seen anything like that in the mock or sample assessment that's come out. Doesn't mean it couldn't be a complex, unfamiliar question or something that's just a bit left of field. Yeah, that's it wouldn't be high on my list if I was cram studying, but you know, I can't guarantee it's not going to be on there. And I'm just checking that formula because if I bring up the formula sheet, see if I can find it. Here we go. So, got the formula sheet up here. Here it is. So the question was that a student was told to use y equals ax plus b, but you can definitely see here on the formula sheet that they're calling b the slope and a the intercept, whereas they've got that the other way around. Whichever one is next to the x would be the slope, and you can see it here. It's bx here. Okay, so I would say they've just switched it around. I sort of talked about this in my stream from last night. Let me find that real quick. I put this picture up. There it is. You'll see there's a bunch of different variations on the way these are written. Okay, so yeah, I'd say that's just what happened. Okay, it's not wrong, but it's not what the formula sheet has. So that's why I'm going with a plus bx. Okay. Yeah, look, there's nothing wrong with doing it the other way around. Yeah, I'm just reading Naomi's comment. Yeah, it doesn't matter, but like, I don't know. I'm just going with what the formula sheet says. So, but you're welcome to do it the other way around. As long as you get the gradient in the right place, I don't mind. Okay. So anyway, hopefully you've calculated those predicted values now. So I got this. Okay, so those are my predicted values. Okay. So, yeah, basically a residual shows how much an actual value, which are these ones here, how much they vary from the predicted model, which we've just done. So what we have to do is find the difference between them, okay? So the formula I write is the residual. I always spell that wrong. The residual is the actual value minus the predicted value. Okay, so that means we have to get, for example, 30 take away 24.6. Okay, 33 take away 35.5. Okay, so we have to do that for each one. Okay, so let's do that. I'm just going to kind of make another table here. Okay, so you can now calculate all of your residuals there. Okay, so all I'm doing is taking the actual number that we were given and comparing it with our predicted model values. Okay, so figure all those out real quick. Okay, this is what I got. Okay, so that's our residual values. Once we've got those residual values, we can now graph it. Okay, so I'm going to draw up my graph. Residual plots always have the x-axis kind of going through the middle. So this x-axis would be time. And then the y-axis would be the residual. Okay. It's really important that you label your axes. There are definitely marks allocated to doing that properly. Okay, so let's go. My x-axis goes from 0 to 4. Obviously, you guys should definitely use a ruler. All right, and then my biggest residual is 6.4, so I'm going to kind of go up to 7 on my axes. Let's make some space here. Okay, so now that I've got my axes set up, we can start graphing. Okay. So at my 0 for x, I need to graph 5.4 on y. That's going to be a there-ish. Okay. At 1, I'm going to graph negative 2.5, which is there-ish. Like I said, obviously you guys should be using ruler and or graph paper. 2 should be negative 6.4. 3 should be negative 1.3, which is kind of on my 3 here. Oh well. And then 4 should be 4.8. Okay. So hopefully you've noticed the pattern that's occurring there. Okay. You have a pretty obvious curve happening here. Okay. Now, what we are doing is doing a linear model. So a curve is very bad, okay? We do not want a curve. If we find a curve, it means we cannot use this model. We would have to use a different one. So you would say something like, no, oh, hang on, a linear model is not appropriate for this data. Right, yes, definitely got some a Hungarian algorithm question coming up next. You can see it's poking up there. Okay, so if it were a linear model, what you would expect is what we call a random scatter. Okay, something that looks more like this. Okay. Okay, so that's a residual plot, and that is how you interpret a residual plot. Okay, so that's a residual plot. I definitely thought, I agree, Hungarian algorithm is definitely worth doing tonight, because I have a feeling in my bones that there's going to be a Hungarian algorithm question tomorrow. So here's one I pinched from the sample IA2 that's on the QCAA website. So I'm going to leave that up there for a second, more than a second, maybe a minute, and let you all have a quick go at it. See if you can get it part of the way there. Okay, so your first step would be to draw that as a matrix. Okay, if you haven't already done so, make sure this goes into a matrix first. Hang on, let me space that a bit better. Okay, so the first thing we do is called a row reduction. Okay, so we look down each row and we find the smallest number. So there's the smallest number in the first row, there's the smallest number in the second row, there's the smallest number in the third row. Okay, so we're going to take that number away from each of them in that row. So I'm going to do take away 11 here, take away 11 here, take away 11, take away 7, take away 7, take away 7, take away 5, take away 5, take away 5. Everyone have a go at doing that. Write the new matrix. Okay, so that was our next step. So that was called a row reduction. Okay, I believe we also did a Hungarian algorithm last night as well. So if you want to see another version, that one's there. Okay, our next step is going to be called a column reduction. Okay, so once again, you're going to look down the columns for the smallest number and take those away. So this one was looking across the rows. This one's looking down the columns. Okay. So here's the smallest number. Here's the smallest number. And kind of all of them are the smallest number. So technically you're taking away 0 from each one, but that does nothing. Okay. Okay, everyone have a go at that. Okay, so that's the row reduction and the column reduction done. Now what you need to do is get a highlighter or a pencil out, and you want to cover the zeros with as few lines possible. Actually, maybe I'll write this first. Okay, cover the zeros with as few lines as possible. Diagonal lines don't count, by the way. Okay, so that means we can do that, and we can do this way. Okay. So it took us 2 lines. Okay. So you can't finish your allocation until the number of lines equal the number of rows How do you spell adjust? I don't know. So we have to do the adjustment, which is the actual Hungarian algorithm part. Okay. So as you can see, we've got 2 lines, but 3 rows, so we have to do the adjustment. Okay. So in the adjustment, you find the smallest uncovered number. And when I mean uncovered number, I mean it's not highlighted. Okay, so find the smallest unhighlighted number. In this case, it's going to be 2. Okay, so subtract it. Subtract that number from all the uncovered numbers and add it to any numbers covered twice. Okay. Okay, can everyone see what I've done there, hopefully? So you find the smallest uncovered number and you subtract it from all uncovered numbers and you add it to any number that's covered twice. Okay, and this one here is covered by both lines, so it's covered twice. Hopefully that makes sense. Okay, let's write our new matrix after that. So do that calculation. Okay. And then we repeat this step up here. So we repeat this. Cover the zeros with as few lines as possible. Okay. In this case, it takes at least 3 lines to do it. Okay. I can't do it in any less than 3 lines. So that means we're finally able to allocate. Okay. So let's do that. So let me just remind myself, this is ABC 1, 2, 3. Okay, and I start making my bipartite graph, which is a graph that has sort of 2 sets of 2 clear groups of vertices. Okay, and now I can start drawing these out. So A can do job 1 and job 2. B can do job 3. And C can do job 1 and job 3. I've just seen your question, Belle. I think it depends on what the context of the question is. Okay. It depends if it's in the deposit phase or if it's partially in the withdrawal phase. So you might need to clarify there. Okay, so I'm looking at my allocations and I can see, well, B's probably a good one to start with because B can only do 1 job. So B is definitely getting job 3. Okay, now that means that C can only do job 1. Okay, so C had the option of job 1 and job 3, but B's taken job 3, so that leaves C with job 1. And if C has job 1, then A must be allocated job 2. Okay, so A, it's team A, I think. No, job 2, I can't lie. And the question may ask you to then go back and figure out the total cost of that. And in this question, they were asking you to consider the original assumption made, the assumption being that they can only do 1 job at a time. obviously, looking at this table, it would be a lot cheaper if Team C could just do everything. So that would be even better. Okay. Yep. Okay. So that's Hungarian algorithm. Yeah. So Belle, your question about annuities there. If it's got a takeaway, then it's probably talking about the withdrawal phase of an annuity. I've got a whole video on annuities, and it sort of talks about the withdrawal phase, so you can go and have a look at that if you like. Okay. All right. So I thought maybe you might want to do a critical path analysis, but I will also have a look at the question Abby sent me real quick. I'm assuming she's done that. So just take a tiny break while I check that. All righty. Always a pleasure. Happy to help. So, Abby, I've just had a look at the two questions you've posted, you've emailed to me. And I know where they're from, and I have the work solutions. So if I don't get to them, I will email you my work solutions to them. So you'll at least be able to see what I've done. Okay. But I don't want to keep you all up all night, because I think it's also really important that you get your sleep. Okay. Okay. So I'm going to wait one more minute, give you a chance to turn this table into a network. Funnily enough, Noah, I actually wish I could do the exam. I'm dying to know what's on it. Like, I kind of have all these weird theories of what I think is going to be on there, but I'm dying to see what's actually going to be on there. I mean, I feel there's going to be a Hungarian algorithm question. I feel there's obviously going to be some time series and some bivariate data, some of those scatterplotty kind of things. Maybe a residual plot. There'll be some sort of bonkers growth and decay geometric sequences question. Yeah, but there's going to be something that's super out there, and I'm dying to see what it's going to be. So yeah, I kind of wish I could actually sit the exam. Okay, I'm going to make a start on my network now, so hopefully you've had a chance to have a go. Oh, you rat bag. Hang on. That's going to be easier. Okay. So that's my network diagram. Hopefully we all got something that looked a bit like that. Any questions? Let me know if you're unsure about anything I just did then. Let me know. Why does D connect to E? Well, funnily enough, D and E don't connect to each other. They're both connecting to the what I call the finish node, the final node. Okay, so you've got to remember in critical path analysis, and I see this a lot. Yeah, I see this a lot. People forget in critical path analysis that the line, the edge, is the activity, not the node. Okay, so the nodes are like checkpoints. The vertices, these dots here, they are checkpoints. Okay, so D is this line here, E is this line here. Okay, so they don't connect per se, they just finish in the same place, which is the completion of the project. Okay, so to say, yeah, you sort of ask the question, why does D connect to E? Well, it doesn't. They both just connect to the end of the network. Okay, so hopefully that answers that question. Okay, and it's time to do our forward scan. So I start here at 0. See, I always think of this as the start checkpoint, and this is the finish checkpoint. Okay, and there's a couple of other checkpoints along the way. No worries. Okay, so I move from left to right through my network, and I'm adding as I go along. If I have a choice between two edges, I pick the biggest one going forward. Okay, so that's going to be 4 there. Now coming into this node here, I either have 4 plus 3, which is 7, or I have 5 just coming from B. So I'm going to pick the biggest one there, which is 7. Okay, and then I come to the end, and I've either got 7 plus 2, which is 9, or I've got 4 plus 3, which is 7. So I'm going to do 9. Okay, that's my forward scan. And the forward scan tells you the earliest start time of each activity. What it means is, for example, D and C cannot start until A is finished. So once A is finished, there's a checkpoint. That's 4 minutes, 4 weeks. And then after 4 weeks, D and C can start. Okay? E can't start until C and B are finished. So E's earliest start time is 7. Okay? Now for the backwards scan, I'm going to start at 9 and I'm going to work my way backwards. Okay? Now, if I find that I have 2 choices, I will pick the smallest number going backwards. Okay, so I'm going to do 9 take away 2 is 7 there. And then back here, I'm going to do 9 take away 3 would be 6. Okay, or I've got 7 take away 3 would be 4. So I'm going to pick the smaller one. And then I've got, coming back here, I've either got 7 take away 5, which is 2, or I've got 4 take away 4, which is 0. Okay, I'm just going to double check that to make sure we're all happy there. Yeah, theirs is going to look a bit different to mine. Yeah, but we got the right answer. We got 9 as our earliest completion time. So that's the soonest time it can be completed. Now, our critical path, and this one. Normally I would say the double numbers, but that's a little bit misleading this time because it doesn't exactly tell you. But basically the path that we took to get to 9. I think that would be it there. Okay. Okay. Now, lots of people do this in different ways. Some people will make like 2 of these little boxes. There's lots of different ways to tackle it. This is just the way I'm doing it. If you've learned a different way, you go for it. Okay. So part B there is to determine any activities that could be delayed or extended and by how long without affecting the minimum project completion time. Justify all decisions made using mathematical reasoning. Okay, so basically any activity that is not on the critical path has float time. So they could be delayed. So D can be delayed and B can be delayed. Okay, so let's do that. Now, like I said, there's lots of different ways to do these, but just the way I find easiest to remember is, let me get a highlighter, the right-hand side of B's right node minus the left-hand side of B's left node minus the activity time. Think of it like a sandwich. You know, these 2 are the different sides of the bread, and 5 is the delicious filling. So I do 7 minus 0 minus 5. Or 7 minus 5 minus 0, doesn't matter. Okay, and now let's do the same for D. Why don't I let you have a go at that first before I do it? All right, if you haven't already done so, here we go. So I'm going to do the right-hand side of D's right node minus the left-hand side of D's left node minus the activity time. Which is also 2 weeks, I believe. Okay, so you would basically conclude, well, the earliest completion time of this project is 9 weeks. Both activity B and D can be delayed or extended for 2 weeks without affecting the minimum project completion time. Okay, so that's what you'd kind of conclude with that question. Okay, so that's your critical path analysis. I'm just having a quick look through chat again to see what people wanted to do. Oh yeah, we want to do some time. Let's do some time series. because apparently there wasn't much of it on the exam today. So that makes me feel like there's going to be a rebound. So let me grab something from one of the mock or samples. We did that one the other day. I'm going to grab that one, but I can't remember if I've already done it. Yeah, okay. I've seen, oh, a tricky geometric question. Oh, that sounds fun. Let's do these time series deseasonalizing first, and then I'll find you a tricky geometric question. Okay, so here we go. We've got some seasonally adjusted rainfall data here. So that means this has already been deseasonalized. Okay, so we don't need to touch that one for now. Okay, we've been given the seasonal indices, lovely, and then we've been given some actual data that's not deseasonalized. Okay, so we need to do that first. Okay, so the first thing we're going to do is deseasonalize some of that data. Okay, so that means for summer, we're going to do 127 divided by the summer index, which is 1.24, like that. Okay, so give that one a shot. I'm going to round to 2 decimal places, like that. Okay. Now I'm just going to add this to my table up here. I don't know if you're allowed to do this in the test or not, but that's all right. I'm not taking the test. All right, so the next one So we've got autumn here. Going to divide by autumn's seasonal index. Like that. Okay, you guys go ahead and do the other two. And let's see if you end up with the same answer as me. How did we go? I got 104.17 for winter and 103.88 for spring. Hopefully we all got those right. Okay, the next thing we need to do, to be able to make a prediction, whenever you see that word predict, you can probably safely assume that they want you to come up with the equation, okay? The equation of the straight line, fit a linear model to it. Okay, so the deseasonalized data is going to be our y variable. We need an x variable. So I just do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The numbers in green are going to be your x variables. So when you enter it into your calculator, each number there is representing a quarter. So you've got 12 quarters there in total. So pick up your calculators. In the table, in the X column, put in the green numbers. In the Y column, put in the blue numbers. Give that a shot. Alrighty, I'm going to my 2var stats. And I'm writing down my equation. Don't forget to, if you're using the same formula as me, which I use y equals a plus bx. Don't forget to swap them around. If you use y equals b plus ax or some other variation, you are welcome to go ahead and do it. Okay. But I personally got the, what is this? rainfall. I'm just going to round to 2 decimal places there. It doesn't really matter. You can do more if you like. For the gradient, I'm going to go to 4 places just because it's a number that's less than 1, so it's good to get some detail there. Okay. That's the equation I got. Did we get something similar to that? Hopefully. You may have chosen to round slightly differently. That is okay. As far as I can see in the marking things, they're not overly concerned about rounding as long as it is consider close convention. Convention, I mean, if it's money, you have to round to 2 decimal places because that's what we do with money. Okay. When I did 75 times, you should have done 75 divided by 0.72. Not multiply. That's probably your issue. Oh, maybe I got that too. Yeah. So I'm just looking at yours, Jacob. You do 75 divided by 0.72. Don't multiply. Okay, give that another shot. Okay, once we've done that, we want to predict the total rainfall for each season in 2025. Okay, so if I go back to this table here real quick, we got to 12 in 2017. If I write another 4, it'll be, so that's 2018, 2019, 2020, okay, can you see what I'm doing there? You're just continuing the pattern like that, okay? So by each time. Okay, so summer, autumn, winter, and spring of 2025 must be terms 41, 42, 43, and 44, like that. Okay. Obviously, you don't have to draw it out like that in a table. You can just, add for each year if you want to, but I'm trying to make it super clear what I'm doing here. I'm extrapolating the line. Okay. So summer 2025, that should be a 5, will be 97.61 plus 0.5993 times, and I think we said 41, didn't we? Yep. Oh my goodness. Okay, so that's the first one. Why don't you guys have a go at doing the rest? Noah asked, how did I get 97.61. I put those, I put back up in the table here, I put all this information into the calculator, I pressed the data button and I entered all that data in, and then I used the stats function in my calculator to come up with the gradient and y-intercept. Okay. Hopefully you know how to use the stats function on your calculator. What X and Y values did I put into the calculator? Yeah. So back up to this table here. The numbers I've put in green, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Put that into the X column, And then once you've done that, put the rainfall data into the Y column. Okay. Good. Hopefully that's all making sense. Feel free to keep putting questions in the comments if you're not sure about anything. Okay, so if you haven't already done the answers to those. Yeah, the quarters, the number of quarters is X and the rainfall values are Y. I'm very glad to hear that you did well on your test today. That's great. Residual plots we did earlier today. So when this recording goes up on my YouTube channel, you can go back and watch it. And we did min, cut, and max flow 2 nights ago because I think we're going to run out of time because I don't like going too much past 9 o'clock because I want you guys to get a good night's sleep. But if you want to quickly check them out, I will. It'll be on this YouTube channel, and I will try and quickly put some timestamps into the description so you can kind of find stuff. But we did residual plots was one of the first things we did tonight, and I've done min, cut, and max flow 2 nights ago, I believe. Okay, so that's what I've got. No worries. All right, so that's deseasonalizing and then using a equation of a line, a straight line equation, a least squares line, they're all the same thing, to be able to make predictions into the future. Okay. All right. Like I said, it's just hit 9 o'clock. So is there any chance you do a hard geometric question pretty sure that, yeah, Oliver, I agree with you. I'm pretty sure there will be a hard geometric one. Let's have a really quick look at one of them that was on the. I'm just going to steal it, or on the mock and sample. There was one about where was it? No, that's arithmetic. Where is the geometric one I liked? All right, so that's one of the ones that was on, I think it was either the mock or the sample, I can't remember which. So sorry if you've already seen it. I said sorry, not Siri. Stupid phone. Okay. So let's have a look at that one real quick, because I saw lots of discussion on the Facebook page about the bird question. Okay. So when things reduce by a percentage, that means it's got to be geometric decay. Decay means numbers going down. Growth means numbers going up. Okay, so whenever you're doing decay, and we had a lengthy discussion about this last night, you have to take them away from 1. So a reduction of 15%, the common ratio would need to be that. Okay. Which is, of course, 0.85 is going to be your common ratio. Okay. So I believe it was something like 17% on the bird question. So you would have had to have taken away 17% from 100 and then use that as your common ratio. Okay. So with this one, you got 2 options. You can either write it as the general formula for the nth term, which, oopsie, doesn't look like that. Looks like this. Times r to the power of n minus 1. Okay, which would then be, that's the first term. And then you would just have to use trial and error to find when it falls below 100,000. Okay. Yeah. The other thing you could do is do it as recursion, which would look like this. Total line. No, I'll just do that. Like that. Oh, great. Yeah, we had a big old discussion about when we add and when we take away from one last night. So hopefully that was helpful for people. I sort of thought, as soon as I heard about that bird question, it was like, oh, I'm so glad we had that big discussion about it last night. Alrighty. So To set up recursion in your calculator, you would type in 600,000 and press enter. That kind of saves it. Then you would hit multiply by 0.85, and then you can continually press enter until you get below 100,000 tons, and just count how many times you had to press enter. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got on the 12th term, it falls below 100,000. Hopefully we all got something like that. Now that's if you're using T0. If you're using T1, it would be the 13th term. Okay, so it depends on how you do that. There are slightly different variations. Either way, the answer is 2019. What do I do on the calculator? Okay, so get your calculators ready. Type in the number 600,000. So 600,000, and then press enter. That kind of stores that value in your calculator. Then press multiply times 0.85. And then you can just keep pressing enter, and it will continually do that calculation until the number falls below 100,000, which for me took 12 presses. Okay, any last questions about that geometric sequence? Excellent. Okay, well, I don't want to keep you up all night because you definitely need a good night's sleep going into tomorrow's exam. But what I will do is I'll really quickly get into those other two videos that those last 2 nights worth of live streams, and I'll try and get in time, like put timestamps in for when we cover different topics so that you can quickly find what you're looking for, because over the last 3 nights we've covered quite a bit of territory. Okay, so I'll get in there and do that real quick now. But do not stay up too late. Make sure you've got a good solid night's sleep tonight. Okay. All right. So I'll say good luck to everyone. And wish you luck for tomorrow. Yes, Abby, I'll definitely send you those solutions. Yeah, always a pleasure, guys. Good luck. Do your best tomorrow. And make sure you have breakfast and coffee as well. Okay. Yeah, good luck, everyone. All right.